In this video, we're going to revisit some ideas like confounding and adjusting for variables, but in the context of categorical data. So this is a pretty famous example. UC Berkeley was concerned about possible discrimination against women in the graduate admissions process, and this data was collected back in 1973. So the most basic question would just be, is there actually an association between sex and whether somebody gets accepted? The data set we're using says sex. I assume they actually mean gender, but I'm just going to say sex to be consistent with the label. Okay, so I've got the Berkeley data here. Let's analyze it using JUMP. So if we're just interested in the relationship between sex and whether or not somebody was accepted, we can use analyze fit y by x, right? We've done that lots of times when we're looking at the relationship between two variables. And JUMP will know what to do, giving it categorical data. It's going to handle that differently than when we had quantitative data. Okay, so we're using sex as our explanatory variable. Accepted is the response that we're interested in. And then we just click OK. And it goes ahead and gives you the mosaic plot. It also gives you a contingency table, which has the counts, but also a lot of different percents in it. I get kind of overwhelmed when I look at all of this, so I'm going to get rid of some of these percents. The ones that are usually most helpful are the row percentages, because that's going to show you for each group, based on your explanatory variable, what the chances of successes and failures are. But I actually don't like the way things are ordered here, because notice that yes is at the top because it's sort of treating no as a success. So to me, this mosaic plot is a little bit hard to read. I'd rather reorder my categories. So let me show you how to do that. I'm just going to go back to the column. I'm going to double click accepted. I think you could also right click it and go down here to the column properties and change the value order. So I'm just going to switch yes and no, reverse the order here and click OK. And I can tell that it worked because I've got a little asterisk next to accepted. That's just telling me that it's been altered. And let me do fit y by x again, but now with the modified variable. Okay, so now we've got yes on the bottom. I think this one is a little bit easier to read. And that makes it easier to see that male students are more likely to be accepted than female students. The acceptance rate is higher, at least. And if I look at just the row percentages, I can see what those acceptance rates are. So for female students, it's 25.17. For male students, it's 44.49. So to answer the question, is there an association between sex and acceptance? The answer would be yes, and that's because the acceptance rates are different, right? Because the acceptance rate for female applicants, I guess they're not really students yet, for female applicants is 0.2517. So that's looking at 113 out of 449, calculating that row percentage, while the acceptance rate for male applicants is higher. The acceptance rate for male applicants is 0.4449. So again, calculating the row percentage, I'm looking at 533 out of 1,198. But maybe that's not the whole story, because maybe male and female applicants are not applying to the same programs. So obviously there were lots of programs at UC Berkeley in this year, but we're just going to look at two to keep things simple, and we're going to call them Program A and Program F. So I basically want to break this down by program. I can't do that using analyze fit y by x because that limits me to just two variables, just an explanatory and a response, but I have a little bit more flexibility with analyze tabulate. So I'm going to do analyze tabulate, and I'm going to start off just by kind of recreating the graph I had with fit y by x. So I'm going to put my response variable accepted up here in the drop zone for columns, and then I've got sex in the rows. So far this looks basically like what I had with fit y by x, but now I want to break it down further by program. So I'm going to take program right here and drag it over on the left side. And now it's sort of like I have two separate two-way tables, right? I've got one for program A and one for program F. And again, I'm going to use the row percentages to calculate the acceptance rate for each combination of program and sex. So I'm taking row percentage here and dragging it up on top of the numbers. And now it's giving me the percentage. So I can see, like for program A, applicants who were female, the acceptance rate was 82.41%, and those who didn't get accepted, 17.59%. So let's go ahead and copy these over. For program A, applicants who were female, 82.41% were accepted. For program A male, 61.94% were accepted. So that's interesting because overall, males were more likely to be accepted, but when we look within program A, we actually see that female students had a higher acceptance rate than male students did. And let's do the same thing for program F. So program F female, 7.04% were accepted, and for program F male, 5.90% were accepted. So it's not just program A, it looks like the same trend is holding up in program F2, right? That the acceptance rates for female applicants are actually higher than for male applicants. Acceptance rate for female applicants are higher, and that's in both programs, in A and in F. So that seems really surprising that overall the acceptance rate for male applicants is higher, but once we break it down by program, the acceptance rate for female applicants is actually higher in both. But this is not so different from what we've seen like in a regression context, right? Where you can look at the relationship and it has a particular slope, but then after accounting for another variable, the slope can reverse. And the explanation is basically the same here too. This happens when you have a confounding variable. So let's think about whether program meets our definition of a confounding variable. So first let's set up a little diagram where we have sex as our explanatory variable, and we're using that to predict acceptance. And we want to know whether program is a confounder. So to meet the definition of a confounder, it would have to be related to both the response variable and the explanatory variable. So I think the association between program and acceptance is pretty easy to see, right? The acceptance rates are much higher for program A than they are for program F. So applicants to program A are much more likely to be accepted. And this counts as an association because knowing which program they're in tells you something about whether or not they're going to be accepted, right? It helps you to predict whether or not they're going to be accepted because program A is so much more likely to accept you than program F. The connection between program and sex may be a little bit more difficult to see, so why don't we create a graph for this? Again, I can't just use fit y by x because that only allows me to look at two variables at a time, but I have more flexibility with the graph builder. So I'm going to go open the graph builder window. And again, I'll start off just kind of by recreating what I had with fit y by x. So I've got accepted on the y-axis and sex on the x-axis. And by default, it just gives you these dots to show how many are in each category, but I can click the button up here to turn it into a mosaic plot. And then if I want to break it down by program, I can take program and put it in the group X box. And now basically I have two mosaic plots, right? The one on the left is showing the relationship between sex and accepted for program A. The one on the right is showing the relationship between sex and acceptance for program F. So based on this, do you think there's an association between sex and program? In other words, does knowing which program someone applied to help you to predict their sex and vice versa? Pause the video here for a second and see if you can describe that association. So here we're not looking at the heights of the bars, we're looking at the widths of the bars to see how the sample sizes are different for males and females. So looking at program A, we can see that the bar for male is much wider than the bar for female. So that's telling us that most people who apply for program A are male. Whereas when we look at program F, it looks pretty even, about the same number of male and female applicants. So there is an association between sex and program because male applicants are more likely to apply to program A. So knowing that somebody is male helps you to predict which program they're going to apply to. So even though the acceptance rate is higher for female applicants, the number of male applicants who are accepted is much larger because there were just way more male applicants in the first place. And if we put this together with program F, we can see that the overall number of male applicants who were accepted is much larger, because if we combine the area of accepted males for program A and accepted males for program F, that's going to be much larger than if we combine accepted females for program A and accepted females for program F. So when we excluded program, we could see that overall the acceptance rate for males was higher than for females, but after we adjusted for program, it reversed. Then the acceptance rate was higher for females within each program. So we've seen that before, that after adjusting for a confounder, the strength and direction of the relationship between variables may change. And that's what's happening here. So after adjusting for program, and adjusting for program, all that really means is that we're looking at the two programs separately. So breaking it down and looking at A and F separately. So after we do that, the relationship has changed and the acceptance rates do not show discrimination against female applicants. The acceptance rates actually are a little bit in favor of female applicants. So of course there's still equity questions that you could ask here. So you could ask, why are there so many more applications from males than females? What are the forces that drive that? Are there societal pressures that push female students away from program A? Things like that. But at least at the stage of graduate admissions, there doesn't seem to be any gender discrimination.